Let us continue our topic to our lesson 3.3 Total Internal Reflection. We have described how light is partially reflected and partially transmitted at an interface between two materials with different indexes of refraction. Under certain circumstances, however, all of the light can be reflected back from the interface, with none of it being transmitted, even though the second material is transparent. And this is possible, like in this figure 3.12a. Okay. Several rays are shown radiating from a point source in material A with index of refraction Na. Several points in this Na are in this material A with the index of refraction Na. The rays strike the surface of a second material, the B, with index NB, where the index of refraction of the A is greater than the index of refraction of the B. And that is, materials A and B could be water and air, respectively. So, for the water, it has smallest Na, and this is an air with unity 1. Okay, so NB is 1, for example, and Na is 1.33. So Na is greater than NB. From Snell's law of refraction, this equation, because Na over NB is greater than unity, sine theta B is greater than sine theta A. The ray is bent away from the normal. Thus, there must be some value theta A less than 90 degrees for which sine theta B is equals to 1. And that is when theta B is equals to 90 degrees. Sine 90 degrees is always equal to 1. And from this figure, you can see that in this line 3, the incident ray is reflected back or has an internal reflection. Okay? Yung ray is hindi siya lumagpas kay material B. Pag titingnan natin dito sa another picture na mas clearer, ganito yung nagiging itsura niya. Nireflect niya yung light, but none of it or some of the rays were reflected back. And this is what we call the total internal reflection. Okay, this is shown in this diagram, which emerges just gazing the surface at an angle of refraction of 90 degrees. So the angle of refraction from the normal, this is the normal, is 90 degrees. The angle of incidence for which the refracted ray emerges tangent to the surface is called the critical angle. So this is the critical angle, again normal to the line. So this is the reflected ray and the normal line of the two materials. So the critical angle is below or within the reflected ray. So this is the critical angle, and the reflected internal ray of 90 degrees is in the another surface or in the material B that has created the 90 degrees angle in here. The angle of incidence for which the refracted ray emerges tangent to the surface is called critical angle, denoted by theta crit. Okay, if the angle of incidence is larger than the critical angle, the sine of the angle of refraction as computed by Snell's law would have to be greater than unity, which is impossible. Beyond the critical angle, the ray cannot pass into the upper material. It is trapped in the lower material and is completely reflected at the boundary surface. And what does it mean? This is the angle of reflection from this line, the angle of reflection and refraction. So, ang sabi dito, if the angle of incidence is larger than the critical angle, okay, angle of incidence is larger than the critical angle, then it will be impossible to have an internal reflection. Kasi, possible daw, kasi beyond the critical angle, they cannot pass into the upper material. This situation is called total internal reflection, and it occurs only when a ray in material A is incident on a second material B, whose index of refraction is smaller than that of material A. And that is, index of refraction of B is less than the index of refraction of A. We can find the critical angle for two given materials A and B by setting theta B equals 90 degrees, and that is sine theta B equals 1 in Snell's law. We then have the equation of critical angle for total internal reflection. And this will be the new equation relationship for the total internal reflection with an angle critical. The total internal reflection will occur if the angle of incident theta A is larger than or equal to the critical angle. Okay, sabi niya, it will only occur if the angle of incident theta A is larger than this is larger than this. Applications of total internal reflection. Total internal reflection finds numerous uses in optical technologies. An example, consider glass with index of refraction n equals 1.52. If light propagating within this glass encounters a glass-air interface, the critical angle is, of course, for a glass-air interface, then the NB is an air, so 1, and the NA is the glass, which has a 1.52 and 0.50. When we will have to solve the critical angle, we need to calculate it using a sine or arc sine and input the value 0.658 in your calculator. You will have a value of 41.1475 and so on. But since it has a 3 significant figure, we can have 41.1 degrees only. Okay. The light will be totally reflected if it strikes the glass air surface at an angle of 41.1 degrees or larger, because the critical angle is slightly smaller than the 45 degrees. It is possible to use a prism with angles 45, 45, 90 as a totally reflected surface. As reflectors, totally reflecting prism have some advantages over metallic surfaces such as an ordinary glass mirrors. While no metallic surfaces reflects 100% of the light incident on it, light can be totally reflected by a prism. What is a prism? This is what our prism looks like. And it says 45, 45, 90 degrees. Now, as reflectors, totally reflecting prism have some advantages over metallic. Okay, I'm done with that. A 45-45-90 prism, used as in figure 3.13a, is called a prism. Light enters and leaves at right angles to the hypotenuse and is totally reflected at each of the shorter faces, just like in this figure. Okay? The total change of direction of the rays is 180 degrees. Binoculars often use combinations of two prisms, as in figure 3.13. Binoculars, okay? Um, from this figure, total internal reflection in a prism, when light enters at 45 degrees or the 45 degrees of the prism, it reflects the light into the another surface that has a 45 degrees in this prism, and then it will reflect it back out. Okay? Ito yung ginagamit sa ating mga binocular, yung ating mga telescopes, and because they can reflect the images or the incident light from the lens outside, then they can travel the light or the images go, and that will go to the eyes of the viewer. Kung ano yung nandito na images, it will be reflected into our eyes without any without any kulang. Kung ano yung image dito, yun din yung makikita natin dito. Ito yung kagandahan ni prism. Now, a bundle of fine glass or plastic fibers behaves in the same way and has the advantage of being flexible. A bundle may consist of thousands of individual fibers, each of the order 0.002 to 0.001 in diameter. If the fibers are assembled in the bundle so that the relative positions of the ends are the same, or mirror images at both ends, the bundle can transmit an image. Okay. So, fiber optic devices have found a wide range of medical applications in instruments called endoscope, which can be inserted directly into the bronchial tube, the bladder, the colon, and other organs for direct visual examinations. They are using this one, inserting into our body, and that they can have a clearer image of our organ inside the body, for they can operate internally. Ito na yung mga advanced technologies ito na yung application niya sa advanced technology natin in the medicine field. A bundle of fibers can even be enclosed in a hypodermic needle for studying tissue and blood vessels far beneath the skin. Fiber optics also have applications in communication systems, in which they are used to transmit modulated laser beam. The rate at which information can be transmitted by a wave, it can either be light, radio, or whatever, is proportional to the frequency. And to see qualitatively why is this so, consider modulating the wave by chopping off some of the wave crest. Suppose each crest represents a binary digit, with a chop off crest representing a 0 and an unmodified cresting representing a 1. The number of binary digits we can transmit per unit time is thus proportional to the frequency of the wave. Just like in this topic, we are talking about reflections of light. In the bundle of fibers, they are transmitting informations, the 0 and 1 binary numbers. Infrared and visible light waves have much higher frequency than do radio waves, so a modulated laser beam can transmit an enormous amount of information through a single fiber optic cable. Okay? Another advantage of optical fibers is that they can be made thinner than conventional copper wire. So more fibers can be bundled together in a cable of a given diameter. Hence, more distinct signals, and for instance, different phone lines can be sent over the same cable. Because fiber optic cables are electrical insulators, they are immune to electrical interference from lightning and other sources, and they don't allow unwanted currents between source and receiver. And for these and other reasons, fiber optic cables play an important role in long-distance telephone, television, and internet communication. Uh, for example of fiber cables is our LAN cable, the LAN cable, which we are using in our internet Wi-Fi portable device. Okay, so next, total internal reflection also plays an important role in the design of jewelry. The brilliance of diamond is due in large measure to its very high index of refraction, n equals 2.417, and correspondingly small critical angle. Light entering a cut diamond is totally internally reflected from facets on its back surface and then emerges from its front surface. Imitation diamond or gems, such as cubic zirconia, are made from less expensive crystalline materials with comparable indexes of refraction. Napapansin nyo when there's a jewelry or kumbaga nagtitingin ng mga fake and original diamonds, they are using tiny tiny parang microscope, and yung mga microscope for them to examine the critical angle, kasi pinapailawan nila yan ng light, and then yung mga reflections of light, doon nila mapapansin kung yung crystal is pure diamond or not.